everyone. Welcome to part 1 of chapter 10. This chapter is all about chemical reactions. So I really like this chapter because we're really starting to do some chemistry, some actual reactions that we can do in the lab. Today's lecture is focused on writing balanced chemical equations that obey the law of conservation of matter. So we'll learn how to write chemical equations, we'll learn how to balance them, and then we'll learn how to take word problems and turn them into balanced chemical equations. I really enjoy this chapter, and I hope you do too. So what are chemical reactions? We've talked about them a bit already when we talked about physical and chemical changes. But chemical reactions occur when a substance is converted into one or more new substances. For example, this silver fork here. This silver fork is just made up of a bunch of silver atoms. But when it reacts with the air, it'll actually react with some of the sulfur that's in the air, and it will tarnish. When I was a kid, I had to help my grandmother polish her silver because it would get dull, right? And so that dullness is that silver reacting with the sulfur in the air to form silver sulfide. Okay, so we know that this is a chemical change, right? A chemical reaction because we're seeing a change in color. So remember those 7 characteristics of a chemical change? One of them was a change in color, and that's what we're seeing here. And so that's our evidence that a chemical reaction has occurred. So chemical reactions cause the rearrangement of atoms, but they don't cause either the creation or destruction of atoms. This is called the law of conservation of matter. We will talk a lot about the law of conservation of matter today. Essentially, just anything that you start with is also going to end up in your products. Okay, so you can't kind of just make sulfur come out of nowhere or make some silver disappear along the way, right? I always like to say that's how we know magic isn't real. It wouldn't obey the law of conservation of matter. So that's what we're saying here. All of the atoms that we're starting with, we also have to end with. The only thing that can happen in a chemical reaction is that those atoms get rearranged. So in chemistry, we will kind of describe all our chemical reactions as chemical equations. So these chemical equations are just shorthand notation for chemical changes or reactions. So we have some parts of an equation. This is our reaction for the reaction of ammonia or nitrogen trihydride with hydrochloric acid to make ammonium chloride. So the stuff on the left-hand side, that's called the reactants. Those are the things that we are putting into the reaction. And so those will be the things that are kind of used up along the way. If you were thinking about this in terms of maybe like a recipe, this would be our ingredients. The stuff on the right-hand side, that's called the products. There may be one product like we see here, or there may be more than one, but they'll always be on the right-hand side of this reaction arrow. And this is what's being produced in the reaction or being made. So like if we were, again, following a recipe, the stuff on the left, that's what we would put in, maybe flour, sugar, butter, eggs, and then the stuff on the right, that would be our cookies. That's what we're making. Anytime you see this kind of chemical reaction, you may find it useful to think of it as a sentence, because we are going to do the opposite later in today's lecture. We're going to take a sentence and turn it into a chemical equation. But you can also think of this chemical equation as a sentence. So here, this would be ammonia and hydrochloric acid react to produce ammonium chloride. Right, so this is kind of a sentence that we see in chemistry. So we have 2 different numbers that show up in these chemical reactions. We've already talked about subscripts when we talked about bonding. Those subscripts show how many of an atom are in a particular molecule. So like if we take water, for example, this is showing us that we have 2 hydrogens and then we don't have anything here, so that's an imaginary 1 oxygen. Right, so those subscripts are telling us how many of each atom are showing up in our molecule. The new type of number that we see in balanced chemical equations are coefficients. This is going to show how many of a molecule you have. So like this here, this is our coefficient. So that's telling us that there are 3 water molecules. Okay, so the number in the front tells you how many of the molecule you have. The number in the middle are telling you how many of each atom you have in that molecule. So if we were looking at this, that coefficient in the front tells us that we have 2 water molecules. But if we were to count up how many individual hydrogens and oxygens we have in this molecule, that 2 is going to distribute in. So just like math, we kind of think about this like that. So we are going to end up with 2 times 2 to get 4 hydrogens and 2 times 1 to get 2 oxygens. So again, in this 2 water molecules total, we're having 4 hydrogens and 2 oxygens. So that coefficient is going to distribute in and get multiplied by those subscripts. So I want you to go ahead and do a practice problem. For these problems, I want you to tell me how many of each atom are in this molecule. Okay, so just like I was just doing with the water, right, where that 2 distributed in, and so I had 4 hydrogens and 2 oxygens, do the same here and tell me how many of each atom I have in each one of these molecules. All right, go ahead and pause. Come back when you're ready to see the answer. All right, so in this first one, again, that 2 is going to distribute, so we're going to have 2 sodiums, and it's going to distribute to the chlorine, so we'll have 2 chlorides as well. For this one, this 3 will distribute. That will give us 3 magnesiums. This one's a little bit tricky. So this 2 that's on the hydroxide is actually going to be distributed in like that, okay? Because that's telling us we have 2 hydroxides. So we already have 2 oxygens and 2 hydrogens. When this 3 also gets distributed, it's going to get multiplied by each one of those as well. So we're actually going to get 3 times 2 oxygens to give us 6 oxygens. And same thing for the hydrogens, 3 times 2 will give us 6 hydrogens. So this distributes to everything in the parentheses, and this 3 will distribute to everything in the molecule. All right, this last one is our trickiest one. So that 4 is going to distribute in, so that will give us 4 berylliums. And then remember, this 2 distributes in as well. So the 2 is going to get multiplied by the nitrogen and the oxygen. So when that 4 gets distributed in, multiplied by the 2, that will give us 8 nitrogens. And 2 times 3 oxygens gives us 6 there, times 4 in the front gives us 24 oxygens. Okay, so just make sure you've got all of the distributing happening. All right, so in a chemical reaction, you'll come across a few symbols. We've already talked about the first one. That reaction arrow is going to separate the reactants and the products. When we kind of say it out loud as a sentence, we'll usually say the word produces or reacts to form or maybe even yields, right? But that's always separating our reactants and our products, and it's going to point at the products. Sometimes you'll see symbols written after our compounds, and that's going to tell us the state of matter of those different molecules. So if it has an S in parentheses, that's going to tell us that's a solid. Usually that's for metals like aluminum and iron and things like that. If it has an L, it will be a liquid. And usually you'll see this, like when we write it, you'll see it as a cursive L so that it doesn't look like an I, okay? But that will mean a liquid. Typically, we will only use this term liquid for 2 substances. We'll use it for pure water or for bromine. Anything else that you think might be a liquid is actually probably an aqueous solution. An aqueous solution, we'll jump down here, means that a substance has been dissolved in water. So let's take salt water, for example. Salt water, we would, kind of in our normal life, think about that as a liquid, right? It clearly looks like a liquid. But in chemistry, salt water is not a liquid, which is weird. Salt water is an aqueous solution because it has salt dissolved in water. So it's a mixture, right? So we will use this aqueous term when we're talking about something that's been dissolved in water. So most of the time, your kind of quote-unquote liquids are not liquids, but they're aqueous solutions. Again, the only things we'll usually use liquid for are water and bromine. And then our last one, which I kind of skipped, we will have gases will be denoted by the letter G. These are usually things like water or carbon dioxide, maybe even hydrogen. A symbol that you might see every now and again is this triangle. We've already encountered triangles in this class, and usually we mean change, right? Like delta T is change in temperature, or delta V would be a change in volume. If you see a triangle above our reaction arrow, so it would look like this. Here's our arrow, and there would be a triangle above it. That means that heat is being added to our reaction. So from a practical standpoint, this would be like if we were doing a reaction in our lab, that means we stuck it on a hot plate or a Bunsen burner, and we heated it, usually to kind of help speed things along. So as we've talked about before, chemical reactions are often using energy or releasing energy, right? So they will likely be endothermic or exothermic. And we can actually represent whether something is endothermic or exothermic as part of our chemical equation. And we'll typically use the term heat. So if it's an endothermic reaction, that means we are putting in heat. So if we're putting in heat, that means heat is being added to our reaction. So we're going to put it as a reactant. Okay, so for an endothermic process, heat is a reactant because we're putting in energy. The opposite is true for exothermic reactions. In exothermic reactions, heat is being released or produced during this reaction. So for exothermic processes, we show heat as a product. So it's over here. So if you see heat on the left, that's endothermic, it's being put into the reaction. If you see heat on the right, that's exothermic, and it means it's being released. You may also see heat as like some number, let's just say 60 kilojoules. So if you see kilojoules, that is also heat. Same thing. So if we said our imaginary 60 kilojoules, it would be the same thing. So if you see kilojoules showing up, that is also heat. Sometimes we'll actually put the number in instead of just writing heat. All right, so in summary, the reactants are the starting material, right? And they're always going to be on the left-hand side. So in this example, our reactants are 2H2O. And you see that cursive, right? Cursive L there would be a liquid. Our products are going to be the substances formed. In this case, we're forming hydrogen gas and oxygen gas. That arrow means produces. It's always going to point toward the products. The coefficients are the number in the front. So these are our coefficients. Subscripts are the numbers inside the substance. Okay, so those are things like H2O or H2 or O2. And then we have phases of matter, and they are going to always be shown after our substance. So they'll be solid, liquid, gas, or aqueous. So here, our reactants are water, which is a liquid, and hydrogen gas and oxygen gas. Alrighty, let's get some practice on this. Go ahead and complete Chapter 10 Lecture Worksheet Problem number 1, and then come back when you're ready to keep going. Alrighty, so I mentioned earlier the law of conservation of matter, right? And essentially, the way the law of conservation of matter plays out is that everything that we start with, we also have to end with. We can't just magically make a hydrogen atom disappear or pull some oxygen out of nowhere, right? We have to start and end with the same amount of stuff. So the way that we phrase this in science is that in a chemical reaction, matter is neither created nor destroyed, okay? So everything going into your reaction also has to come out. So we say that if an equation obeys the law of conservation of matter, it is balanced. Okay, we're going to talk a lot about how to balance our chemical equations now, but the whole reason we have to balance them is so that they obey the law of conservation of matter. And I'll show you what I mean by that. So if we look at this reaction, right now, on the reactant side, we have CH4 and O2. So here's our depiction of that. Our carbon is black, and so we have one carbon atom, we have 4 green hydrogens, and we have 2 red oxygens, okay? If we look on the product side, we're making carbon dioxide and water. So this is our carbon dioxide, and we have our water, okay? So we have 1 carbon atom, 2 hydrogens, and 3 oxygens. So looking at this, we have the same number of carbon atoms on both sides, right? We have 1 carbon atom on both sides, but we have different amounts of hydrogens. On the left-hand side, we have 4 green hydrogens, and on the right-hand side, we only have 2. So at some point, we did some magic, and we made 2 hydrogen atoms just poof, disappear. Can't do that. That disobeys the law of conservation of matter. Oxygen is having the opposite problem, right? We had 2 oxygens on the left-hand side, and now we have 3 on the right-hand side. So somehow we just made some oxygen out of nothing, which again, you can't do. So this does not obey the law of conservation of matter. So we say this is unbalanced. Okay? So to know that we have a balanced chemical equation, we'll do what I was just doing here is I'll total up how many of each type of atom I have. If the types of atoms and the number of atoms are the same on each side, then that's balanced and it's obeying the law of conservation of matter because all of the atoms that we start with are also going to be all of the atoms that we end with. Okay? If this reaction wasn't balanced, like the one on the previous slide, the way that we fix it is we add coefficients in the front to balance our chemical equations. Okay, so coefficients allow us to obey the law of conservation of matter by making the number and type of atoms the same on each side of our chemical equation. So like this. So we've added a few coefficients here. Whoop. My apologies. Our coefficients that we've added, sorry about that. Our coefficients that we've added are a 2 here and a 2 here. So those 2's are allowing us to obey the law of conservation of matter. So by doing that, that 2 distributes in, right? And so does this 2. So now we have 4 oxygen atoms on this side, and we have 2 plus 2 here, right? 2 oxygen atoms on that side. So there's 4 oxygen atoms on each side. Okay, the same thing will happen now with our hydrogens. We had 4 hydrogens here, and now we have 2 times 2 gives us 4 hydrogens there. So by adding these coefficients, we multiply them in to allow us to obey the law of conservation of matter. So now we have the same number and type of atoms on each side of our reaction arrow. All right, some rules to follow when we're balancing chemical equations. The first one, and the most important one, is that matter cannot be created or destroyed. That's the whole reason that we're balancing chemical equations. We have to obey the law of conservation of matter. Our second one, subscripts cannot be added, removed, or changed. I like to say that subscripts save lives. For example, this molecule we all know. That's water, right? H2O. Okay, well, what about this one? What if I changed one of the subscripts, right? So now we have a 2 there. So is this still water? Nope, right? Now this is hydrogen peroxide. So this one, you drink it, you live. This one, you drink it, you die, right? So I like to say that subscripts save lives. You cannot change the subscripts. If you want to change the number of atoms in your compound, then you need to put a number in the front instead. You can only change coefficients. You cannot mess with the subscripts. And then another thing that I sometimes see people do is coefficients can only go in the front of chemical formulas. They can never go in the middle. So like if I wanted to have 2 water molecules, I would put the 2 here. You can't like do this. I've seen people do that sometimes. You can't do that. Okay? You can only put numbers in the front. Here's some more tips for balancing. If this seems overwhelming right now, you might want to kind of screenshot this or take a picture, maybe write it down, to save these tips for balancing once you get a few under your belt, because these will help. But this is kind of the process that we're going to go through as we're going to get better at it. So our first one is to identify all types of atoms, like I did in the previous example. We had carbon, hydrogen, and oxygen on both sides of our chemical equation. And I wrote those below our reaction. Then I went and figured out how many of each atom I had on each side of the reaction. Okay? When we're going to go through and start balancing, we want to start with the atoms that only appear once on each side. If you have something like hydrogen or oxygen that appears multiple times on a side of an arrow, do those last. They will normally sort themselves out along the way, but if you try to start balancing things that show up in multiple places from the beginning, it tends to just make your life really hard. So start balancing with, something like calcium, like a metal, right? Things that are only going to show up in one place on each side of the arrow. Then we're going to kind of put coefficients in, change our atom count as we go until everything evens out. And then at the very end, we're going to double check our answers, make sure everything looks good. Okay, so this stuff at the top, that's going to be kind of our general what we're doing. Some extra tips, again, once you get better at it, these will be even more helpful. Try balancing big formulas first. Like say you have like calcium hydroxide or magnesium phosphate that's got a bunch of atoms in there. Do those first and then save like individual elements, like if you have oxygen gas or hydrogen gas, so elements by themselves, do those last. If the same polyatomic ion ends up on either side of our arrow, we can actually treat that polyatomic ion like an element, but it has to stay together on each side of the arrow. And I'll show you what I mean by this a little bit later. And kind of most importantly, I'm going to show you one way to balance it, but there's not really like a right way. Some of them are harder, some of them require a little bit of creativity. You'll kind of find your own groove on how you like to balance chemical equations as we go. So I would recommend kind of start off doing it my way, but if you find a way that you like better, feel free to do it that way. Let's try this one. So first thing we're going to do is figure out how many of each element we have on either side of our reaction. So on each side we have iron, oxygen, and hydrogen, right? Iron, oxygen, and hydrogen. And I like to write them in the same order on each side so I can really easily see, how many of each element I have. So on the left-hand side, I have 2 irons, I have 3 oxygens, and I have 2 hydrogens. On the right-hand side, I have 1 iron, 2 hydrogens, and 1 oxygen. Okay, so as we can see here, we're not balanced, right? We have different amounts of iron, different amounts of oxygen, and we do have the same amounts of hydrogen, which is lucky, but we don't have the same of anything else. Okay, so let's go ahead and figure this out. I like to start with the metal atoms first. That tends to be the most easiest to me. So in order to balance our irons, we're always going to put a coefficient in front of the one that is smaller. So we only have 1 iron on this side, so I'm going to put something here to multiply by that 1 to give us the same number as the left-hand side. Since we have 2 on the left-hand side, this number is going to be a 2, and we're going to change this now to be a 2. So now as you can see, our irons are now balanced. So let's go ahead and look at our oxygens. I have 3 oxygens on the left-hand side, but only 1 on the right-hand side. So again, I'm going to multiply the smaller number by something to make it equal the bigger number. So I'm going to put this 3 out front, so that 3 gets multiplied to the oxygen. So now we have 3 oxygens on the right-hand side, just like we do on the left-hand side. However, by putting that 3 there, I also changed my amount of hydrogens. So now 3 times 2 gives us 6 hydrogens on this side. But that's a pretty easy fix because I can put a 3 here now and give myself 6 hydrogens on this side as well. Okay, so again, you're just going to kind of put coefficients in the front and kind of play around with it until you get your numbers to match. Let's try this one. So on each side, we have phosphorus and we have oxygen. On the left-hand side, we have 4 phosphorus and we have 2 oxygens. And on the right-hand side, we have 2 phosphorus and 5 oxygens. So again, we're going to need to multiply these by something to get them to even out. Like I said, I usually recommend doing oxygen and hydrogen last, so let's go ahead and balance our phosphorus first. So we have 4 phosphorus on the left and 2 phosphorus on the right. That means this needs to get multiplied by 2, so 2 times 2 will give us 4. When we do that though, we change the number of oxygens because this also distributes to the oxygen. So 2 times 5 gives us 10 oxygen. So now, in order to balance our oxygens, we are going to multiply this side by 5 to give us 10 oxygens on the left-hand side as well. So then we can look, we see we have 4 phosphorus, 10 oxygens. This is balanced. Let's try another one. So now we have nitrogen and hydrogen on each side. Okay, actually, let's go ahead and have you pause here. I want you to try this one out. Pause here, see if you can give it a go, and then come back when you're ready to see the answer. Alrighty, let's go over this. So on the left-hand side, I have 2 nitrogens and 2 hydrogens. And on the right-hand side, I have 1 nitrogen and 3 hydrogens. Again, I usually recommend doing oxygen and hydrogen last. So here, let's do the nitrogens first. So in order to balance our nitrogens, I'll put a 2 here. So 2 times 1 will give us 2 nitrogens. When I do that though, that 2 also distributes into the hydrogen, so we end up with 6 hydrogens because it gets 2 times 3. So in order to balance our hydrogens, we need to stick a 3 here. So we get 3 times 2 will give us 6 hydrogens. Alrighty, let's try this one. This one is trickier, okay? This is a combustion reaction. We're going to learn about types of reactions a little bit later. But I want you to recognize that this is a combustion reaction because it'll always show up exactly the same way. It'll be something with carbon and hydrogen, and we call this a hydrocarbon. So something with carbon and hydrogen will react with O2 to produce carbon dioxide and water. And these last 3 pieces, they will always be the same. That's how you'll recognize it as a combustion reaction. The only thing that will change is this one in the front. But just so you know, these combustion reactions are the trickiest to balance, okay? So I'm going to recommend you always balance combustion reactions in the exact same order, okay? Balance them as carbon, and then hydrogen, and then oxygen every single time. The reason we want to do oxygen last is because oxygen shows up in 3 different places, and it tends to be tricky to balance. So always do it in carbon, hydrogen, oxygen in that order, and you'll meet with a lot more success. All right, let's try this out. So we have carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Okay, so on the left-hand side, we have 1 carbon, 4 hydrogens, and 2 oxygens. And on the right-hand side, we have 1 carbon, 2 hydrogens, and do you see we have 3 oxygens? We have 2 here and 1 here, so we've got 3 total. All right, so for now, our carbons are balanced, but our hydrogens are not, okay? So in order to balance our hydrogens, we need to put a 2 here. So we get 2 times 2 will give us 4 hydrogens. So they balance. That also changes our oxygen count though. So we have 2 oxygens plus another 2 here, and that will give us 4 oxygens. So that means we just need to put a 2 here. So that gives us 4 oxygens on the left-hand side as well. This was a fairly straightforward combustion reaction, but I promise you, some of them can be pretty tricky. Alrighty, I want to talk a little bit about simplifying in equations. So let's look at this reaction. I want you to just think about it for a second. Is this reaction balanced? So our answer is, yeah, the reaction is balanced, right? There's 4 hydrogens on each side, and there's 2 oxygens on each side. So it's balanced. Okay, well, what about this one? So again, yeah, it's balanced, right? There are 8 hydrogens on each side, and there are 4 oxygens on each side. So this is balanced too. Do you see it's the same chemical reaction? It just has different coefficients? Okay, so they're both balanced, but if you did this one, I would actually mark you wrong. Not completely wrong, but you may lose a point or 2 because your reaction isn't simplified. Do you see all of these coefficients can be divided by 2? So in order to simplify it, we just take all of our coefficients, divide them by 2, and then we would get this reaction. Okay, the top reaction is simplified. So just make sure when you're doing this balancing that you look and see, can my reaction be simplified? Can all of these numbers, all of these coefficients be divided by the same number? If yes, then do it to simplify your equation. Alrighty, I want you to go ahead and get some practice balancing chemical equations by completing Chapter 10 Lecture Worksheet Problem number 2. Once you're done, come back and we'll keep going. So, like I mentioned earlier, sometimes we will encounter word problems in chemistry. Like this one here. This says to write the balanced chemical equation for when magnesium reacts with oxygen to produce magnesium oxide. So we need to take these words, this description of a chemical reaction, and turn it into a balanced chemical equation. So the first thing, just to kind of sort out our thinking, is to write a word equation. So let's see, we've got magnesium reacting with oxygen to produce magnesium oxide, right? So all of those different pieces are telling us something, right? So we have magnesium reacting with is essentially telling us plus, and it's reacting with oxygen. So both of those are our reactants. Magnesium is reacting with oxygen. Anytime you see to produce, that's telling us there's an arrow, okay? It's telling you write an arrow to show what the products are, and it's producing magnesium oxide. So all we've done now is right now picked apart the important parts of the sentence and kind of written them down to start to make our chemical equation. So magnesium plus oxygen gives us magnesium oxide. Our next step is to write the unbalanced equation with the correct formula for each substance. So magnesium here is a single element. Anytime you see a single element, I want you to think, does it show up in Hofbrinkel? Remember Hofbrinkel? I hope you do. So here's Hofbrinkel. So remember, Hofbrinkel tells us the diatomic elements. So when we look here, we're like, okay, magnesium does not show up in Hofbrinkel, therefore magnesium can sit by itself. Oxygen though, oxygen is a member of Hofbrinkel. So anytime you see oxygen, that will be a diatomic element. So we will write that as O2. So all Hofbrinkel is doing is telling us whether or not our element needs a 2 when it's sitting by itself. Okay, so magnesium is not diatomic, but oxygen is. And then our last one is magnesium oxide. Magnesium oxide is a compound, and it's an ionic compound. Okay, so this is going to require you to remember nomenclature. Yay, right? I know you guys all love that chapter on nomenclature. All right, so magnesium oxide is an ionic compound. It's made up of a metal and a nonmetal. Anytime you see an ionic compound, I want you to think it's made up of ions, so I need to write them out. So magnesium is Mg2+, and oxygen is O2-. So since these charges are equal and opposite, they cancel out and we get MgO. So that is our skeleton equation. Mg plus O2 gives us MgO. Okay? Make sure anytime you see an ionic compound, you always write out the ions and circle and switch. So after we've gotten our unbalanced chemical equation, then we can balance it. So right now, just looking at this, do you see we have 1 magnesium on each side? But we have 2 oxygens on the left and only 1 oxygen on the right. So that means we are going to need to add a 2 here to balance our oxygens. So now we have 2 oxygens on the left, 2 oxygens on the right. But now our magnesiums are no longer balanced. We have 1 on the left and 2 on the right. So we'll add a 2 here to balance our magnesiums, and we'll get our balanced chemical equation. Okay, so this was our first example. Let's try another one. All right, this says write the balanced chemical equation for the decomposition of potassium chlorate to give oxygen and potassium chloride. So again, our first step is to kind of pick this apart and figure out what's actually happening. So you can kind of read this as blah, 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 blah. Oh, potassium chloride. Okay, potassium chlorate is decomposing. Usually if you see something is decomposing, that means it's sitting by itself and it's going to kind of fall apart in the reaction. So potassium chlorate, to give, that's the same as saying to produce, to yield. That's going to be our reaction arrow. So potassium chlorate gives oxygen and potassium chloride. So we'll see this as oxygen plus potassium chloride. You'll notice that I've written these in a different order in this problem. That was intentional to show you that these can be in either order. You could have written oxygen and then potassium chloride, or you could write potassium chloride and then oxygen. It doesn't matter which one comes first as long as they end up on the correct side of the reaction arrow. So in this instance, as long as they are both products, it doesn't matter the order that you write them in. Okay? All right, so we have potassium chlorate reacts, right, to gives potassium chloride and oxygen. Anytime you see an and, that's our plus sign. Okay, so now we need to write our unbalanced equation by turning these words into chemical substances, right? So potassium chlorate is an ionic compound. Potassium's a metal, chlorate is a polyatomic ion. So we have K plus and ClO3 minus, okay? So we have a 1 plus and a 1 minus. Those directly cancel out, so we're just going to put them together. Potassium chloride is also an ionic compound because it's a metal and a nonmetal. So we find, okay, potassium's K plus, Cl is 1 minus, so we get KCl. And then oxygen, remember, Hofbrinkel, right? So that's a single element. Does it show up in Hofbrinkel? Answer, yes. So our oxygen is going to be O2. Okay, so there's our reaction. KClO3 gives KCl and O2. So our last step is to balance the chemical equation. Okay, this one is a little bit trickier to balance because if you look at it, our potassiums are balanced, our chlorides are balanced, but our oxygens are not. There's 3 on one side and 2 on the other. And sometimes this will trip people up because they say, well, what can I multiply it by? There's nothing, you can't multiply something times 2 to give you 3, right? Because it has to be a whole number. Anytime you see a 3 and a 2, you are going to multiply them both by something to make them equal 6. Okay, so sometimes you have to go to the lowest common multiple. Okay, so in this case, I'll multiply this by 2 to give 6 oxygens on the left-hand side, and we'll put a 3 here to give 6 oxygens on the right-hand side. Once we do that, though, our potassium and our chlorine are no longer balanced, but we can fix that pretty easily by putting a 2 there. So that will give us our balanced chemical equation. Alrighty, let's try another one. This says write the balanced chemical equation for the reaction of butane, and I gave you butane, with oxygen, where carbon dioxide and water are the only products. Okay, so a little bit different. This says that butane is reacting with oxygen. So we know those are going to be our reactants. And then it says the products are carbon dioxide and water. This was written in a little bit of a different order, but if you read it and kind of talk about it out loud, I think you'll start to figure out what the pieces are. So we have butane and oxygen are our reactants, and carbon dioxide and water are our products. All right, now we need to go through and figure out the chemical formulas for each one of these substances. I gave you butane, that's C4H10, and then we found oxygen again. Remember, oxygen is a single element that shows up in Hofbrinkel, so it's diatomic. And then we have carbon dioxide and water. Carbon dioxide is a molecular compound, right? We see dioxide. So even if you didn't know what carbon dioxide was, you could see, okay, there's no prefix in front of carbon, so that's just a C. And then dioxide is telling us O2. Okay? The way that we recognize this as a molecular compound, you can do one of two things. First, they're both nonmetals. Therefore, this is molecular. Second, we see a prefix in this molecule. The only time that we use prefixes is when we're talking about molecular compounds. So one of those two should clue you in. And then we're familiar with the formula for water. All right, so that's what we've got. C4H10 plus O2 gives us CO2 and H2O. So this is a combustion reaction. Do you see that we have something with carbon and hydrogen, reacts with oxygen to give carbon dioxide and water? It's always going to follow that exact same pattern. The only thing that's going to change is this. Okay, so remember, when you balance combustion reactions, I recommend doing carbon, then hydrogen, then oxygen. So in order to balance our carbons, we have 4 on the left and only 1 on the right, so we'll put a 4 here. That will balance our carbons. Then we need to go through and balance our hydrogens. So we have 10 on the left and we have 2 on the right. So we're going to put a 5 here to multiply that 5 times 2 to give us 10 hydrogens. Now, this is where it gets a little bit interesting. Do you see that on the right-hand side, we have 4 times 2 gives us 8 plus 5 oxygens gives us 13. So I need to figure out, okay, what goes here to multiply to give 13? And the answer is nothing, right? We can't multiply something by 2 to give us 13 because 13 is an odd number. So that's just not going to work. So a lot of times, that's why I told you combustion reactions can be a little bit tricky because they'll do this weird like odd number thing. Anytime you get into that weird situation where you have an odd number and you're not sure what to do, you're going to go back and double all of the coefficients except for oxygen. So you're going to put a 2 here. You're going to make this, instead of 4, this is going to be 8 now. Instead of being 5, this is going to be 10. Okay, so now if I went through and re-added up our oxygens, we have 8 times 2 gives us 16, plus 10 oxygens in water gives us 26 oxygens total on the right-hand side. So now I can put a 13 here, so 13 times 2 gives us 26. So again, anytime you run into a situation where you have an odd number of oxygens on the right-hand side in a combustion reaction, just go back and double all of the coefficients you've done so far. That will always sort itself out. Alrighty, let's try another one. This says, write the balanced chemical equation for the reaction of magnesium hydroxide and phosphoric acid to form magnesium phosphate and water. So this is written pretty straightforward. It says magnesium hydroxide and phosphoric acid are reacting to form magnesium phosphate and water. So anytime we see and, that's going to be a plus sign, and the to form will be our arrow. So magnesium hydroxide and phosphoric acid to form magnesium phosphate and water. All right, so now we need to figure out what everything is. So magnesium hydroxide is an ionic compound because we have a metal and a polyatomic ion. Magnesium is Mg2+, and hydroxide is OH-. So when we circle and switch, right, those are not equal and opposite, so that 2 needs to go to the OH. So we'll get Mg, and since this is a polyatomic, we'll put hydroxide in parentheses, and that 2 will go on the outside. Okay. Phosphoric acid, if you don't remember how to name acids, this is kind of your time to review. Phosphoric acid, anytime we have an ic acid, that came from an 8 polyatomic ion. Remember, I ate something icky. So phosphoric acid came from phosphate. So phosphate is PO4 3-. And remember, we're just going to add enough hydrogens, H+, to balance out that phosphate. So that 3 is going to go to the hydrogen, and we're going to get H3PO4. Okay, magnesium phosphate is also an ionic compound. So again, we need to write out our ions and figure out our formula. So magnesium and phosphate, we already figured both of those out from the reactant side. So now, again, those are not equal and opposite. So the 3 is going to go to the magnesium. So we'll get Mg3. And that 2 is going to go to the phosphate. Since phosphate is a polyatomic ion, we'll put phosphate in parentheses. And then finally, and water. All right, so now we've got all of our substances written out, and now we can go ahead and balance our chemical equation. Okay, so you remember right when we were talking about balancing chemical equations, I said something about the polyatomic ions, and if they stayed together on each side, then you could treat them as elements. That's what I'm talking about here. So if you look, we have a polyatomic ion of hydroxide, but hydroxide doesn't show up on the right-hand side as hydroxide, so we can't do this with hydroxide because it doesn't show up on each side. But phosphate does. We have phosphate here and phosphate here. Since the phosphate stayed together, we can balance the phosphate polyatomic ion just like we balance elements. Okay, so let's go ahead and do that. On the left-hand side, we have one phosphate, right? We have one PO4. But on the right-hand side, we have two phosphates, two PO4. So I'm going to put a 2 out front so that now I have 2 phosphates on either side of our reaction. All right, now let's go ahead and look at magnesium, because I told you most of the time I like to do hydrogen and oxygen last. Okay, so magnesium, there's only one magnesium on the left-hand side, but there's 3 magnesiums on the right. So I'm going to put a 3 here in front of magnesium, so now I have 3 magnesiums on each side. So now we need to look at our oxygens and our hydrogens. When we do this, I'm not including the oxygens that were in phosphate because we balanced those phosphate oxygens as phosphates. So when I'm talking about oxygens right now, I'm not talking about those. So on the left-hand side, we have 2 times 3 will gives us 6 oxygens, and we only have 1 on the right-hand side. So I'm going to put a 6 here to balance my oxygens. And now let's count up our hydrogens. So in magnesium hydroxide, we have 6 hydrogens, and in phosphoric acid, we also have 6 hydrogens, for a total of 12. If you look on the right-hand side, we have 6 times 2 gives us 12 hydrogens. So this is balanced. Alrighty, time to get some more practice. Okay, go ahead and do Chapter 10 lecture worksheet problem number 3, but for now, only write the balanced chemical equations. We'll come back and do the other stuff later, but I want you to get some experience writing these word problems because that's probably the trickiest part of this chapter, is taking those words, remembering how to do bonding, writing balanced chemical equations, right, and doing all of that, making sure they obey the law of conservation of matter. Think about this review of nomenclature as helping you to review for the final. Remember, our final in this class is cumulative. So even though that chapter on nomenclature was quite a while ago, you're going to need to know it all for the final anyways. So think of this chapter as helping you to remember. Okay, this is the end of this lecture. Okay, we did cover a lot of ground today. We learned about writing chemical equations, just in general. We learned about the parts of chemical equations, and we learned about why we have to balance them to obey the law of conservation of matter, right? Matter cannot be created or destroyed, so the same number of atoms has to show up on either side of our chemical equation. And then finally, we learned how to take word problems and turn them into balanced chemical equations. And like I said, I think that's probably the trickiest part of this chapter, so do take some time to practice doing it. As always, if you have any questions or you're, a little rusty on bonding, whatever it is, please feel free to send them my way. I am more than happy to help you out, and I really like this chapter. This is probably one of my favorites. I really enjoy balancing chemical equations because I think it's kind of like a puzzle, and we're starting to put together all of these different pieces of chemistry so that we can do really cool reactions and other types of calculations in lab. So this chapter in this particular lecture is definitely one of my favorites. So if you have any questions, please feel free to reach out. I am more than happy to help. Otherwise, keep working hard, and I will talk to you guys next time.